In this video, we're going to talk about Chapter 4 over Introduction to Systems of Differential Equations. And in particular, in this video, we'll just cover Section 4.1, First-Order Systems and Applications. So what we've been doing, if we kind of look back where we've been, we have talked about how to solve a particular set of differential equations. For example, we talked about linear differential equations, separable, homogeneous, Bernoulli, et cetera, and then we've been talking about homogeneous versus non-homogeneous differential equations with constant coefficients, but we haven't talked about systems of differential equations. So we're going to talk about a very particular set of systems of equations, namely ones that can be used or that can be solved using substitution, and so that's kind of where we're heading today. In particular, we're going to talk about a system of two first-order equations. And in this first definition, you'll notice that we have two different differential equations. We have external functions f and g, which are just generic to say that we'll have relationships between x, y, x prime, and y prime, and then the independent variable t. And then we'll have a separate one, which is being denoted with g. We are making the assumption that all of the derivatives are with respect to time. So I'll just kind of highlight that right there. All of these primes are with respect to t. So our goal is to identify how to take a system of two differential equations and be able to solve it using the methods that we learned from Chapter 3. So first of all, what does it mean to be a solution of a system of DEs? So what it means is you're going to find a pair of functions, x of t and y of t, that satisfy both equations identically, right? So this means that you're going to plug both x of t and y of t into the first and the second differential equation, and they will both satisfy those differential equations. In this section, we're going to learn how to solve simple systems via substitution. So very similar to algebra, where you have a system of two equations and two unknowns, you can solve for one unknown and plug it back into the other. That same concept is what we're going to use here. So let's take a look at 22. We have two DEs, both of them very simple. And what I'm going to do is I'm going to arbitrarily choose to look at this first DE. And I'm going to say, all right, if I know that x prime equals 8y, then I could also say that x double prime equals 8y prime, just by taking the derivative of both sides. But I also know that y prime is equal to negative 2x. So I'm going to replace this y prime with this expression. So now I conclude that x double prime equals 8 times negative 2x, or in other words, x double prime plus 16x equals 0. And so what I've done is I've reduced this from a system of two differential equations to a single second order DE. So again, just to kind of point out, maybe call your attention to this in a different color. This is a set of two first order DEs. And then through this process, I have now obtained a single second order DE. So through this substitution process, I did pay for it by raising the order of my DE, but still, we spent an entire chapter, Chapter 3, learning how to solve these DEs. And so even though we went up a degree, we still know how to solve this. So we set up the characteristic equation. We get r squared plus 16 equals 0. So our roots are plus and minus 4i. So what we have here is that our function x of t is given by a cosine of 4t plus b sine of 4t. Now it's really tempting to just box this in and say, yeah, I'm done. I just found x of t. But remember, we're not just solving a single DE, we're solving a system. So we need an x of t and a y of t, and together as a pair, that serves as the general solution of the system. So now what I'm going to do is I'm going to look back at that original DE that I started with, x prime equals 8y. And I'm going to say, okay, so in other words, y of t is 1/8 of x prime of t. So I can identify the second solution there, y of t, by utilizing the first derivative of x of t. So that's going to be 1/8 of a negative 4a sine 4t plus 4b cosine 4t. And so then in the end, I have y of t equals a negative 1/2 a sine 4t plus 1/2 b cosine 4t. And so I'm going to box that in as well as my x of t. And those two together are going to form the solution. Now I do want to make one note here. Right out of the gates when I got started, I chose to look at that first DE, that x prime equals 8y. And by making that choice, then it kind of set up how I was going to set up my solutions from here on out. You can equivalently work with the other DE first. So I won't run through the entire setup. But if instead we decided to look at y prime equals negative 2x, then following that same method, I could say y double prime equals a negative 2x prime. And then I would look back up at my other DE where x prime equals 8y, and I would say, okay, y double prime equals negative 2 times 8y. And in other words, I get y double prime plus 16y equals 0. So you'll notice here the similarities that we got right here in this line and up here in this line. So we're going to solve it the exact same way. In the second method, our y of t function is going to look like our x of t above, and our x of t will look more similar to our y of t. And so at first glance, you might say, well, how are these actually the same? If x and y are not the same thing, but why are their solutions looking the same? If you go back up to our solutions over here, notice that they are both in terms of sine of 4t and cosine of 4t. So the underlying base functions are the same. The only things that are going to change are these coefficients. And so if we solve it using this second method, yes, our general solution is going to look a little bit different. But had we had initial conditions and we went through and solved for a and b and negative 1/2 a and 1/2 b, regardless of which way we set it up, our final coefficients would be the same either way. So the bottom line here is pick one of those equations, start with it and work with it and go, and then whichever way you do, it'll flush out the same in the end. All right, so along those lines, let's take a look at the next example, which is an initial value problem. All right, so we want to find the particular solution, and all this is saying is you want to find the general solution and then solve for C1, C2, or A, B, C. So, and solve for coefficients. All right. So I am just going to randomly choose to work with this function here. So I'll recopy it. X prime equals negative y. And so if I take the derivative on both sides, x double prime equals negative y prime. And then, of course, substituting in for y prime a 10x minus 7y, I get x double prime equals negative 10x minus 7y, or x double prime equals 7y minus 10x. Okay, so right now I have a second order DE right here, but the bad news is that I have x's and y's mixed in. So I can't at this moment use my methods from chapter 3. However, if I look back to that first DE that I was using, I had x prime equals negative y. So in other words, y is negative x prime. So I'm going to transform this by plugging in negative x prime for y. So x double prime equals negative 7 x prime minus 10x. So x double prime plus 7x prime plus 10x equals 0. So here's where I'm at. Now I have a second order DE with constant coefficients. I can set up my characteristic equation. R squared plus 7r plus 10 equals 0. And that factors to r plus 5, r plus 2 equals 0. So r equals negative 5 and negative 2. All right, so from here, I can set up my x of t function. And I'm just using a's and b's rather than c1 and c2 just because that's how the book does it, but you can use c1 and c2 if you like. So I have an a e to the negative 2t plus b e to the negative 5t. And now how am I going to find my y function? Again, remember that x, whoops, back a stroke here. Remember that x prime equaled negative y. So y of t is x prime of t, negative specifically, which is going to be a negative 2a e to the negative 2t minus 5b e to the negative 5t. All right, and so now I have my setup for x of t and y of t. Now I want to utilize my initial conditions right here. So let's plug those in. What I know is x of 0 equals 2, and x of 0 is a plus b. And I also know that y of 0 equals negative 7, but that is 2a plus 5b. All right, so now we're back into the standard system of two equations, two unknowns. Use your favorite method to solve. I'll just substitute. So a equals 2 minus b. Negative 7 equals 4 minus 2b plus 5b. So 3b equals negative 11. B equals negative 11 thirds. It's an ugly number, but it's a number nonetheless. And a is 2 plus 11 thirds, which would give me 17 thirds. So now I'm just going to plug a and b back into the equations that I had found up above. So my x of t is 17 thirds e to the negative 2t minus 11 thirds e to the negative 5t. And then similarly, y of t will be, I want 2 times a, so that's going to give me, what, 34 over 3 e to the negative 2t. And then I want 5 times b, so minus 55 thirds e to the negative 5t. And so these two equations together are going to form my solution to this system of DEs. All right, not too bad. So I have a few notes here. In general, it's fairly easy to solve first order systems of DEs. And if it's not easy to solve it by hand, computers can solve it for us. So it's preferable that we work with systems of first order DEs. So let's suppose that we have a super complicated single DE. So in other words, a single nth order differential equation. What we might like to do sometimes is take this higher order DE and write it as a system of first order DEs. That can reduce the computation or runtime if we're going to plug it into some kind of computer algebra system to solve. And so there's a very algorithmic approach for doing this. What we're going to do first is we're going to define a variable x1 equals x. Now I want to point out something that's going to seem very obvious, but it's going to be important. This is an assignment, but this right here is not a DE. All right, so the reason why I'm pointing this out is when we want to write out our system of DEs, we do not include this as our system. So what this step is for is to just set up your variables. So next, what we want to do is we want to identify how we can express the first derivative. So if x1 was equal to x, then the first derivative is the derivative of x1, and we're going to call that x2. So what we have is this guy right here that I just circled. That is a first order differential equation. And then we can continue this process. Well, the second derivative would be the derivative of x2 that we just defined, and let's call that x3. And then we're going to go on down the line until we define xn. All right, and then we don't want to go any further. So again, we're looking at an nth order differential equation. We want to define up to xn. And now what we want to do is we want to list our system of DEs. So again, I already noted we're not going to include this in this step because it's not a DE, but we have this first DE showing up here, the second down here. This one is our second to last DE. So where did this last one come from? Well, remember that we're working with an nth order differential equation. That means we have an nth derivative. And so what we're going to do is, since we only defined up to the n minus first derivative right here, to get to the nth derivative, which is what we want, we're going to take the derivative of this term xn, but instead of writing it as this kind of basic DE, we are going to utilize the function that we have in our original DE. So right now this is a little bit abstract, but it's gonna flush itself out when we do an example. So I just want to emphasize once again, and I'll change the color of my highlighter just to really make it pop. I do not need to go a step further just so that I define that nth derivative. So we'll take a look at this step here in particular when we do our next example. Something that I didn't state up above here is that we can also set this up if we have a system of DEs. So if we have a system of two higher order DEs, we can then go through and write them as a whole system of first order DEs. So we'll see some examples in that case. All right, so let's take a look at number 6. This is a single DE, and you'll notice that it's fourth order. We want to transform it to a system of first order differential equations. So here's our goal, to come up with a system of first order DEs. All right, so just to get started, let's define x1 to be our dependent variable x. I'm going to emphasize yet again, this is not a DE. So when we finally write out our system, we will not want to include this. But now let's define our next variable x2 to be the derivative of x. And that is in fact based on our previous equation x1 prime. So that is one differential equation. x3 is going to be the second derivative, which is the first derivative of x2. I will write in parentheses that this is, actually let me, whoops, went too far back. I will note that yes, this is the second derivative of x1, but I don't actually care about that because I'm trying to set up systems of first order derivatives. So this doesn't really help me. So while it's a true statement, it's not helpful. All right, so now remember I have a fourth degree or a fourth order differential equation. I want to define up to x4, which is the third derivative, which is going to be the derivative of x3. I do not want to go all the way up to my fourth derivative. Stop at the third derivative. So now let me go through these. And again, I don't want to include this one in my system, but these three are all system of DEs. So what I have here so far is I have x1 prime equals x2, x2 prime equals x3, and x3 prime equals x4, but this isn't enough because I haven't gotten to my fourth derivative. So now what I'm going to say up above here is, okay, well, what is my fourth derivative? Well, for one, it's going to be the first derivative of x4, but on the other hand, looking back up here, I can say that the fourth derivative of x is cosine of 3t minus all of that garbage on the right-hand side or on the left-hand side. All right, so I'm going to transfer that stuff down here. All right, but I'm not quite satisfied because I want this final DE to be in terms of a system of first order. So I don't want this x double prime, for example. And in fact, I don't really want any of these here. I want them all to be in x sub I terms. So what I'm going to do is I'm going to rewrite my cosine. I can keep my 6. And what is x double prime? Well, here it is. It's x3. And what is x prime? Here it is. It's x2. And what is x? That was x1. So finally in my system, I'll write down that x4 prime is equal to cosine of 3t minus 6x3 minus 3x2 plus x1. All right, and so this guy right here forms our system of first order DEs. All right, so we have a total of 1, 2, 3, 4 equations to form our system. All right, so 14 is an example where we're actually given a system of 2 second order DEs, and we want to rewrite this system of 2 order DEs as a larger system of first order DEs. So we're going to start out the same as we did in the previous problem, where I'm going to define x1 to be x. And again, this is not a DE. Do not include it in your system. So next, let's find x2. Let's call that the first derivative. And that is also the derivative of x1. All right. Remember, this is a second order DE, so I'm going to stop at x2. However, I do know that my second derivative can be written as a negative 3x prime minus 4x plus 2y. And I'm going to come back to this statement here after I set up my y's. So next, let's set up our y's. I'm going to start similar with my x's, that y1 equals y. This is not a DE, so don't include it in your system. y2 is going to be the first derivative, which is y1 prime. And then I want to stop here, but I would like to identify what y double prime is. According to this previous equation, y double prime is the same as y2 prime, but then according to this DE up above, it is equal to cosine of t minus y double prime minus 2y prime minus y plus 3x. And so I suppose up here, I forgot to write that this is actually x2 prime. So go ahead and add that in right there up above. All right, so now that we have defined x, x prime, y, and y prime, go back up to those two last equations and replace all of these guys with what they should have. So instead of an x prime, let's write that as x2. Instead of an x, we'll write it as x1. And instead of a y, that becomes y1. And then same right here. So this is cosine t minus, whoops. Let's correct this. We don't need this guy over here. So we want cosine, right? There we go. Okay, we already have y double prime over there, so I didn't need to subtract it over. This becomes a 2y2 minus y1 plus 3x1. All right, so now we're ready to write out our system. And in your homework, I would like you to explicitly write this system out. So even though you have it set up here, I want to make sure that you understand which of these form the system and which do not. So for a system, we have x1 prime equals x2, and then we also have x2 prime equals a negative 3x2 minus 4x1 plus 2y1. And then for the y's, we have y1 prime equals y2, and y2 prime equals cosine t minus 2y2 minus y1 plus 3x1. All right, and so these four first order DEs are going to form the system here. All right, and that's problem 14. So there's just one definition here on the next page that we'll include in this video, and then we'll leave section 4.2 for the following video. And so that last definition here is just talking about solution curves. So we've been focusing on how to find a solution of a system. And again, the solution is comprised of two functions, x of t and y of t. If we think of them as parametric equations, much like what we talked about in Calc 3, we can graph them, and that'll give us what's known as the solution curve or the trajectory. So that could be a straight line, it could be a parabola, it could be something much crazier, right? It could be a limacon, or it could be a rose or a cardioid. So sky's the limit on what it could be, but here we're talking about some kind of a curve in the XY plane. So putting those together and graphing them will give you the solution curve. All right, so that's it for section 4.1. So you can look for the next video here to discuss section 4.2.